Today we are having our webinar on heat of hydration effects in concrete placements and theory and application with Dr. Nihal Vitarana. He did one lecture in 2 weeks back also regarding insight into pile designs. And I would like to invite President ISL, Dr. Kamal Laksiri, to have a few words about this lecture.
Okay, thank you. Good evening to all of you, and Dr. Nihal Vitaran, thank you very much accepting our invitation. I think, as Bhanaka said, you conducted the lecture 2 weeks ago with amidst your busy schedule, then you agreed to conduct one more, and also this is not the end, so there will be more to come. And I think more we have listened to him, and he's a veteran in this subject, and especially in the dams, and he has conducted very interesting programs. So I hope this will also be an eye-opener and interesting program for our engineers. And today, I think our Civil Engineering Section Committee Chairperson, Engineer Kamala, is attending to a family function, and so normally she is there. So she asked me to join. So without taking further time, let's start the proceedings. And on behalf of all of us, let me thank Dr. Nihal again, my good friend, for accepting our invitation and helping us with your expert knowledge to enhance our engineers' knowledge. Thank you very much. Nihal, over to you. Yes.
Okay, thanks, Kamal and Bhanuka, for organizing this one. You said this is not the last. My wife said she's going to divorce me if I do any more talks, so I'll have to. This should be the last. Anyway, we got about 75 slides to go through, and so it has to done in a quick way. It's close to 10:30 here. So what I am trying to say is insight. I'm not going to teach anybody how to do thermal stress modeling, but just give an insight so the attendees or listeners can themselves decide, are they doing the right thing or the wrong thing? If the right thing, you can say, that idiot tried to tell us things we know already. If it is a wrong thing, probably you can just think of it in a more rational fashion before you touch concrete. So please go to the next slide. Yeah, why I am not sharing slides today is last time an uninvited guest got in, and he or she start drawing pictures on the screen. So I gave it to the Colombo people to handle it this time. So what is the aim of this presentation? This is an insight only, as I said. It's not, it's not a lecture or university lecture. During what happened when concrete is hardening, basically it's coming into life. So proper understanding of overall mechanism is very important, even especially for young engineers who are now very quick to Google 2 words, and they are very happy with the 2 answers they get. In our days, we look at a manual page by page, we go through, and we tend to learn a lot than Googling or iPading. The third one is most of the big projects now, wastewater treatment plants, dams, transport projects, are now D&C, design and construct, as opposed to projects. People I used to, my days, 3 to 4 decades ago, where owners do engineering themselves. So if something goes wrong, it's always stay in the family. Like, family member does a crime, they all stay in the family. But now it is different. D&C, you have got 2 things. Not too conservative, because the contractor is losing money, and if too risky, if the project go pear-shaped or bad, the contractor will come and take the money after the consultant. So it's need to know what you are doing, not what somebody else told you. Now, I always put merely following a standard. When I put that, few people say, oh, we are doing to British standards, we are doing to European. What's wrong? Probably some Sri Lankan thought they are getting things from the colonial era. British standards not bad, but when it comes to thermal stress, you have to understand they're in cold weather, probably studying on a blanket and write things. So when you pour concrete in Colombo, you start somewhere on 30 degrees and different cement as well. So merely following whatever the standard or Syria, what's that, C663, C660, now I think 760, just in the one numeral, doesn't mean you're off the hook. So what I'm trying to say is no need to parrot things just because somebody else said. When it comes to concrete or any engineering, you have to know what you are doing. All days it works, they all in the family and boss will look after you, and otherwise boss will get into trouble. Next one, please. And my background very quickly. In fact, I did my PhD in structural engineers, temperature-induced stresses in concrete storage tanks, and of course on bridges. And then I was lucky to get an industrial fellowship from the Japanese Academy of Science to work in Hokkaido, the most northern island in Japan, very cold, working with contractors and consultants for 2 years, mainly the heat of hydration and seismic liquefaction. Then I work on few committees, AS3735 and New Zealand 3106. They both are water retaining structures codes, which takes thermal effects very seriously compared with European standards. They just take a nominal reinforcement amount. And 3600, that's a concrete code, and called Australian National Committee on Large Dams, Concrete Dams Technical Committee, and Japanese Concrete Society on heat of hydration as part of rewriting the design and construction specifications. In my career, I have seen good and bad projects. One is when people think heat of hydration, they think they are 10-meter thick walls. Now, heat of hydration affects thin members as well. Bad one is sometimes I still see nightmares witnessing a client or consultant writing a blank check, probably a blank check for a contractor, where diesel probably current price would be Australian dollar 1.5 billion, where some thin members had cracks going right through the thickness, and this is inaccessible over 120 years once we built it. And also I have seen a headstock of the beam where the headstock is the piers or the piles connected. They crack radially as if expanding inside. Next one, please. Now, I just thought if once I announce it, Bhanuka sent me this paper. I think those who from Sri Lanka should have a good look at that paper after this presentation. It's a very good attempt to get things order, but there are a few things probably they missed. And it's about 3.5 meter high, involves 6,500 cubic meter of G50, grade 50 concrete at 56 days. And it got 35% fly ash with a total cementitious content, that is Portland cement plus cement, about 470 kilogram per cubic. It's a very, very rich mix. Now, I had to say Bhanuka is the one master of ceremonies here, happened to be he's a master of ceremonies, so I can't say bad things about the project. Now, the maximum measured temperature was still 85 degrees. So when it is 85 degrees, people have to be very careful. There's a mechanism called delayed entrite formation. That means at about 70 degrees, hydration stops. So when it comes in contact with water, it expands again. So that's a very bad mechanism to have. Luckily here it is too thick. Probably water will not get to the middle, for a long time. Now, his attempt has been based on traditional approaches with limits on average and differential temperature. What I said is, even in Australia and still most part of the world, they say criteria on this specs is maximum temperature rise should be less than 25 degrees. Differential inner to outer is 20 or 25. That's all they do. Then some take further and say, don't worry about the temperature. We put a lot of steel. That's what CESC 660 do. I have seen concrete walls designed using that guideline by modern engineers, where a bumblebee in Sinhalese Dembara or Bambara can't go through that much steel, but still it cracks. Then ask why it cracks. We use CESC 660, but still crack. So probably they rely on the divine intervention, God's blessing. That's not good. It says, that paper say, it caught my eyes. It says Sri Lanka has no criteria on differential temperature, unlike in developed countries. So when I saw the developed, I've been living in a developed country. I just thought, what does it mean? So let's go to the next one, please. So this is his steel cage. You can see it's heavily reinforced. I think in 40mm diameter bars, I haven't seen a 40mm diameter bar for a long time. So I thought it must be heavily reinforced for some reason. So that's how it looks like. Next one, please. Now, his reference to developed countries. I think developed countries get that wrong too. So I have seen both few around the world and here too. Here get this too, wrong too. So no point doing things in Colombo saying, oh, developed countries have guidelines, so we do this one, but developed countries get it wrong as well. That's what I make money sometimes. So I have seen developed countries 400mm thick wall in a D cell, probably 1.5 billion in today's value due to wrong generic spec. As I said, we need maximum cement, 25 degrees, 20, poor specs, basically like parroting copied from somebody else, inexperienced, probably never seen wet concrete, wrote the specs, contractor poured that 400mm thick wall, designed to Series C660. You can see the crack. When I was asked to, I can basically put a ballpoint pen through that one. So I just showed you developing countries won't get heat of hydration correct either. Let's go to the next one, please. So developed countries. So some argue, or cracking, still they are arguing, cracking doesn't accelerate corrosion. So don't worry about the crack with 0.3 or 0.2. Let's put the desalination or bridge project aside. If you got a bathroom, do you get cracks where you can see the cracks? You won't accept that. You ask the builder to redo it. So why arguing that, okay, big projects don't worry about 0.2 or 0.3? So why I put that, it sets in other deteriorative mechanism as well, such as alkali aggregate reaction, where water will go through the cracks and accelerate. This is initially cracked due to heat of hydration. After 8 years, it looks very ugly. So I just don't rely on those people try to sell you snake oil saying don't worry about the crack width. If you write this spec, crack width 95 percentile should be less than 0.2. That's what it should be. After cracking, I have seen the contractors, their specification for the crack repair is thicker than the design report, because they expect poor concrete cracks. They take truckloads of epoxy and start grouting. So I have seen 550 pages crack repair, but the design is over 30 pages. Let's go to the next one, please. Now, I thought rather than jumping into the heat of hydration, I'll just show two types of thermal stresses. One is ambient, hardened concrete. If you got a car park, it will get heated. So that's called ambient due to solar radiation and ambient temperature. Then the second one is heat of hydration. So related to thermal and the heat of hydration affects thermal and durability issues very early. So there are standards like American Concrete Institute Committee 217. They are very good references. That they were the document used by US Army and USBI, Bureau of Reclamation, to build a lot of dams. So they got a lot of experience on those ones. Then the Japanese standard for DNC, there's English version as well. Seria C660, and on ambient you can see two water retaining 3735, 3106, and ACI, American Concrete Institute 318. I suggest especially Sri Lankan audience and the others look at, if they are involved in water retaining structures, look at 3735 and 3106. Temperature effects are very comprehensive. Next one, please. Now, ambient thermal effects. I just, that's happening in hardened concrete. Of course, wet concrete will be subject to ambient too, only, but formwork will mostly cover it. Now, over the years, if you take ambient temperature effects, they normally govern all the loading conditions. 30, 40 years ago, they were not in any standards. So let's go to the next one. Please. I just thought this is how the ambient temperature gradients, ambient condition induced temperature gradient on bridge decks. If you look at 1969, it's a uniform, but now it is a fifth order parabola. Now, fifth order parabola, I did some work with a guy, late Professor Nigel Priestley at University of Canterbury. Throughout the world, they use the left one, right one now, parabola. It is done in New Zealand. So you can see it changes uniform to fifth order parabola. Let's go to the next one, please. So from those two that diagram, 1969 uniform 20 degrees. So if it is a bridge deck, it expands uniformly. If it is on bearing, it's stress-free, no stresses at all, because if it is axially unrestrained. But post 1977 has a fifth order nonlinear parabolic thermal gradient. This one, even if it is unrestrained, we get primary or residual stresses. And if it is restrained, we get secondary flexural stresses. You had sometime what I said, primary residual. Most engineers, when they use software, whatever I won't tell the software brands, sometimes they don't even know what the residual stress is, but they do MIDAS, everything. Sometimes they have no clue. So best thing is to get a pen and pencil and do hand calcs. I don't have time to put that slide today, but that's what you have to be very careful when you get a nonlinear gradient. Next one, please. So in case of water retaining structures under ambient, pre-1977, nothing, doesn't mention. Now both Australian and New Zealand standards said, if tank full under solar radiation, we get 30% temperature right externally. And if it is in winter, we get 20 degrees drop. So once you do calcs, you can see this dominates the hydrostatic induced loadings. Next one, please. So I just put this and a quick example on the water tank. I published this paper in ACI Structure in 1999. The top one is the hydrostatic loading, bending moment, hoof force, circumferential moment, and the vertical force. Middle one and the bottom are the thermal stresses. It's not time to read the numbers. You can see the difference when it comes to circumferential, 0 on the hydrostatic, but thermal effects dominate. So that's some reason why a lot of tanks in Canada and New Zealand start cracking. That's the reason they look at what is post-cracking and they find is the thermal stresses. Again, next one, please. Now I put this one, I put it on the pile foundations too. When a structural member subject to induced loads, that is temperature or swelling and shrinkage, they are effective only on the serviceability. But if you do it as ultimate limit state, because somebody else said in the code, it will overkill, it will kill the job. It's very expensive. Probably send the contractor bankrupt, and the guy's foreman will curse everybody involved. So it is because from this diagram under serviceability, you can see horizontal axis. I put the deformation corresponding y-axis larger stresses, but at the ultimate, it is nothing because ultimate the structure is in plastic stage. So thermal loading or shrinkage is not significant. And at early age concrete, one other thing come into picture. I will put in the slides later. Early age member creeps. It's a semi-solid. It creeps a lot. So if you calculate using elastic theory, when you include creep effects, the elastic calculated value will be reduced by up to 60%. That's one reason some people tend to overestimate heat of hydration effects. Next one, please. ambient versus hydration-induced thermal stresses. As I said earlier, ambient conditions, temperature induced under constant Young's modulus. Concrete has already hardened. So when the sun goes down, they will disappear. But when it comes to early age, thermal stresses are generated under changing Young's modulus. So when it expands in the heating cycle, very low Young's modulus. So compressive stress is very low, but when it cools down under higher stress. So that's what we get, a net locked-in tensile stresses. So two mechanisms are entirely different. Next one, please. Now this is a schematic illustration of the difference. So if E were constant, hydration is equal to ambient induced thermal stress. As I said, hydration induced stresses are occurring mainly because of change in E from low in the low value in the heating cycle and higher value in the cooling down. So in this diagram, quickly the top one showed time versus Young's modulus, because Young concrete E value increases and it goes to asymptotic to the E constant hardened concrete. And then you can see the temperature rises and drops. For the next net effect in the bottom diagram is under changing E, we get initially compressive stresses, compressive positive here, and negative tensile. And the other one on the bottom is tensile strength gain. It starts from 0 to tensile strength. So if those two crosses each other, you get thermal cracking. So it's a simple illustration of this. Is on ACI paper we wrote some time ago. So you have to keep in that mind the reason why we keep the temperature drop in Young concrete or concrete pour is to keep the temperature drop lower when it is on the cooling phase coming to its resting temperature. Next one, please. Okay, now we get to the subject. So I got, the basic difference between ambient temperature and heat of hydration. Same mechanism. Main is in high heat of hydration, E changes with time and very high creep stresses, very high creep behavior. Okay, next one, please. Now, need a well-considered game plan. So it's not somebody set in a book. And I don't think most universities, as far as I don't even teach nowadays how to calculate temperature, dry shrinkage, or induced stresses. They all go with how to design the bridge beam to European or whatever the standards, and ask students to parrot every clauses, but they never teach what most graduates will face inside, how to pour concrete. Now, seamless combination need chemistry, physics, structural, and durability, because durability is governed mainly by what's happening in concrete in the early age. We know now things like alkali aggregate reaction has a big root going back to the early age thermal behavior and temperature regime. Now, heat generation when you pour concrete, heat generation and heat transfer, heat is lost to the environment, are concurrent. They happen at the same time. Now, point 4, concrete changes from liquid to solid in 14 to 24 hours. Structure changes as well. We put the footing first. When it hardens, we put walls. So structure is not linear either. But normally, when you do structural design, you get a completed structure. Here now you get pieces. So you had to look at how each piece affects the other one. And also temperature affects the strength, maturity. Inside the large pore, concrete gets strength at a faster rate than the surface. Being semi-solid, higher, as I said, non-linear creep. Please don't ignore that one. I'm going to touch on that one here too. And also bad preservation. If the structure is cracked at early age, they think it's a bad product. Next one, please. Basic facts on hydration. Most guys know this one. I said hydration is exothermic. That's it. Reaction produces heat. That's what you can see at site. When you touch hydrating cement, it's hot. So it produces heat. Reaction produces heat. Epoxy mode. Rule of thumb is 11 centigrade for each 100 kilogram of Portland cement in the mix. So if you put 300 kilogram per cubic meter of concrete, you get 3 times 33. So at 20 degrees, 20 plus 30, 53 degree absolute temperature. And hydration is thermally activated. It's like chemistry or physics, I can't remember. Some reactions are thermally activated. That's a reaction is occurring faster when the temperature is higher. So why I said that in a larger concrete, inside is much hotter than the outside. So inside hydrates faster than the outer zone. So we need to keep that in mind because some people think everything is adiabatic. And hydration characteristics are unique. You can't just take a concrete mix in England or Spain and apply that to Sri Lanka or anywhere else on the planet. Just every factory is different. They come in different fineness, different aggregate properties. Everything is different. And thermal stresses are produced with or without external restraints. If without means non-linear. So when the gradient is non-linear, even if it is unrestrained, you will get stresses locked in. So the non-linear effects give always the primary stresses. That's the reason why we tend to put a control on differential temperature gradient. Probably the case with the ITC Tama in Colombo as well. They are chasing differential gradient because Sri Lanka doesn't have, developed countries have, but developed countries have too, but sometimes they get that wrong too. Next one, please. Now, validity of temperature along criteria. Most people still, they say specs, if you take 20 degrees maximum, 25 degrees maximum, but temperature is only one parameter. Concrete cracks when thermal stress exceeds the tensile strength. So temperature is only one criteria too. If you look at basics, thermal stress is simply E alpha delta T. E is Young's modulus, alpha is coefficient of thermal expansion, delta T is temperature change. So we only worry about delta T. We don't worry about alpha. We don't worry about E either. So, with this, the cure for all the ailments, so like panacea temperature alone can give problems. Therefore, temperature alone as a sole criteria, example, as it said, has limited validity when it comes to serious projects. It may have a place when 3-4 decades ago, when only 4 cement types throughout the world, but everybody got different cement. It's like milk. Here I can buy about 32 types of milk. So the cement is like that too now. So as I said, 3 to 4 types. You can see American Concrete Institute, AC, civil engineers, they always 3 to 4 types. Therefore, in modern construction engineering, we had to be very careful using those 25 and 20 criteria, because even if they are exceeded, the concrete may not crack. But sometimes they have not been exceeded, they still crack because uncertainty on those, mainly from the construction speediness as well as the different cement types. So what I am trying to say is that we should look at more into thermal stresses versus tensile strength. In Japanese construction, when I worked 25 years ago, it's mandatory the contractor produce that thermal stress prediction versus tensile strength. They don't use that 25 and 20 degree criteria at all. Next one, please. Now, adiabatic versus non-adiabatic reaction. Adiabatic is no heat is lost or gained. So if when some reaction happens, when you say adiabatic, all the sides are closed, shut down. So the heat produced by the reaction itself accelerate the reaction. But when it comes non-adiabatic, it's anything other than above adiabatic. So when I said anything other. There could be isothermal in a thin member. Ambient temperature is 15. Hydration takes about 15 degree temperature environment. And number 4, semi-adiabatic, as I said, is a test now getting very popular. Hot box trial. We make I think 1 meter by 1 meter and pour concrete thermocouples and measure it in Sri Lanka. I was involved in the Nalanda Dam project. I think we wrote a paper in 2015. Irrigation department engineers, I just told them hot box, they did an excellent job. I think the engineer now is a regional manager in Anuradhapura. So there are things, you don't have to look for a calorimeter, adiabatic calorimeter, or when I said isothermal, there's a hydrometer where cement reacts under constant ambient temperature. So isothermal. Even here, if we say isothermal, we used to have those at CSIR, or it's a scientific organization like most of the British Commonwealth countries have. They even don't have that equipment now. So, here we talk about fast construction. Most of the fundamental research organizations have disappeared from the planet. So next one, please. So steps in thermal stress calculation. These are the steps I'll go through on the next slides. I can't remember how many more. So number 1, hydration model. That's the first thing we had. What is it? Are we using the correct hydration model? Then heat transfer. How do you do heat transfer modeling? Then assemble ambient data. Ambient interaction is important, especially in hot weather and cold weather countries. Then thermal properties of concrete, just to give what are the thermal properties. If you Google, you get any number you want. Then its strength and its stiffness gain in young concrete, and thermal stress calculation and comparing with tensile strength. So let's get in. Next one, please. Next one, please. Step 1, hydration modeling. How cement is going to produce heat. Yeah, that's the first one. And most popular traditionally adiabatic, as I said, is a test they do in the lab. No heat is allowed to loss from the hydrating cement and measure the temperature wise. It's easy to use and have worked well, and probably until recently, but now we find it is not doing that job what it was supposed to do. As outlined before, adiabatic hydration model does not reflect on the reality, except in the middle of a thick concrete placement, like a thick dam. Everybody doesn't build dams. I know Dr. Kamal is building some dams. He was supposed to send me some drawings for 3 weeks. Next one, please. This is adiabatic model. So ACI 207, which I said is a very good document. I still got a hard copy here. It had been used for many dam projects in USA and around the world in the Epson of project-specific mixed trials. These are the 4 cement types. They are rapid hardening, slow hardening, sulfate resistant, and normal Portland cement. So in this one, temperature produced by the heat generation itself accelerate the reaction, but it represents only what would happen in a thick dam or something like that, but not in 2000 or 200 millimeter thick walls. So we had to be. I will show you later why it is not correct. Next one, please. Now, Japanese Concrete Institute, again on the adiabatic, they give this formula. It's quite handy, and different cement types, you can get the parameters, but again, it's not for somebody to go and design. It's a very good when somebody doing planning type estimates. And when we do heat of hydration modeling, we want to get the rate. The top one is total heat generated at a given time. As you can see, when time goes to infinity, Qt become Q naught. That's ultimate. And if good with mathematics, you can integrate it and you can get the rate, that is joules per cubic meters per second at a given time. So it's quite good standard what Japanese got. Next one, please. Yeah, this is again Japanese. I got there some values and just produced this one a while ago. So we can get for planning purpose or conceptual level effect of different cement types. And this again, so it gives y-axis time and the temperature in centigrade. Okay, next one, please. Now, what I said, cement, you have to be very careful. What I said here, if cement is too fine, normally I think Portland cement particle is 0.1 millimeter in diameter. But nowadays, you get people sell called slags, you know, SCM is supplementary cementation materials. They say slag, blast furnace slag, fly ash produce low heat. You have to be very careful. If they have ground it too fine, it produces more heat than Portland cement. So this is again Portland cement. This is from the American Concrete Institute. It shows the finer the cement, reaction is faster, but ultimately the total cement heat produced is the same because finer cement got a larger surface area for a given mass. So you have to be very careful when you use somebody else's model, Syria or whatever it is, and do your projects in another part of the world, because each cement mill is different. They do different things. Next one, please. And highest place in temperature, again, as I said, showed in that curve, higher the temperature, rapid reaction. So because the higher the temperature, starting temperature, is reaction taking at elevated temperature, and hydration is thermally activated. So when two things it does, in reality, hydration is rapid, and also when you come to thermal stresses, if you place it at a higher temperature, say 30 degrees, and at night resting temperature is say 20, on top of hydration, you got 30 minus 20, 10 degrees drop as well. So people think the placing temperature is only for hydration. No, it ultimate stress as well. I'll show you it later. Next one, please. Now, varying temperature models, as I said, adiabatic apply everywhere in any member, dam or wall is incorrect because hydration is thermally activated, and adiabatic only replace one special case. Now, there's a couple models, that is heat transfer and heat generation are coupled. So you had to do heat transfer and generation in one hit rather than taking somebody else adiabatic and put it to your finite elements, what you call is transfer and midas, everything. It's the pointless. If I were you, I would buy some beer and drink it. Here in Australia, we get 5 cents back. So no point using the wrong hydration model and try to do fancy analysis. So there have been models, Priestley and Thurston, 1982 in New Zealand, started when they were pouring the Christchurch airport hangar 5 meter thick. They developed that one. Then I happened to do that with Dr. Sakai in Sapporo. And our model is simple, but again, we got the idea from a Danish chemistry scientist, Trastrup, in 1954. Probably, you know, I was in my pants, nappies that time. So we just used that and developed a model and tested that in the lab as well and in practice as well. So this model is a simple computer algorithm to incorporate into heat transfer modeling, but most software can't do it. But so you had to do a little bit juggling. Next one, please. Now I am prejudiced. From my model, I have a lot of ego always. So it is in 1995 conference on concrete under severe conditions. This is cited in British standards as well. I think Syria, whatever it is, C660. I recently saw some Canadians suggest that too. So it basically does it. When you do heat transfer in whatever the model you do, it calculates the heat temperature times heat series, time versus temperature in the concrete, and incorporate that into the model, hydration model, by calculating a TE. T is the equivalent time. So equivalent time at a higher standard temperature, say 2 hours, in elevated temperature, it could be equivalent to about 4 hours. So it's that's how it is coupled. So rather than going into detail, this is how it is done. It's Rastrup in 1954 produced similar chart, similar thing for cement in Denmark. Next one, please. As I said, but now why was there accurate modeling? ITC tower probably too. So some modelers do sophisticated heat transfer modeling, despite hydration models are all low. It's like playing dart in the dark. You can pick any curve from here. So in basically you put rubbish in and get rubbish out, you know, and produce something which is not worth anything. So these ones show the isothermal, constant temperature hydration, bottom 3, and the top 6 are 2 different adiabatic models for the same mix. I haven't changed anything. So look at any numbers you can get from this chart. So if we are using, probably we need to something like a coupled non-adiabatic model, which I mentioned earlier. Next one, please. Step 2, heat transfer modeling. Now, what I thought is, of course, there are software, but just show what heat transfer. Now, this figure I got from another consultancy I did recently on water tanks and ambient, but I don't have resources to draw new ones for the presentation. I took that. What is meant by interaction with the ambient? Traditionally, it's ignored. You know, they just temperature only. Sometimes solar radiation can affect the top surface of raft foundation concrete. So daytime, if you leave it open, sometimes it helps reduce your differential, because the solar heat will heat it up. Especially other one is in cold weather. So if you take a wall, in this case, don't worry about the water side. We get direct solar radiation from the sun rays or sunbeam, then ambient temperature increases. And also if it is a wall, we get reflected. If there are other light or bright buildings around, they send the radiation back to this one. So ambient interaction is very important, especially for surface zones like differential temperature, as well as on thin members. Next one, please. Yeah, this is just a heat transfer mechanism. You know, don't worry about the water side. Other side, you can see outside surface, we get solar radiation, and also then we get the temperature loss due to the convection. If there's a wind or wind blowing past the wall, it takes away a lot of heat. Even under 0 wind speed, there will be heat known as convective heat loss. Next one, please. Some of these can be done in software, but I just want to show you how things are, you know, basic things, what is involved. And you don't need to do a 3-dimensional heat transfer. If you draw it on a piece of paper, you can see heat is losing, it's find the easiest path to dissipate itself. It's like similar to electricity seepage. Draw that. If you got a thin graph, don't run into a 3-dimensional finite element modeling. Just it's always going to be 1-dimensional. Some dams it can be a little bit complicated, but still 95% in my case is just 1-dimensional heat transfer. Even if you look at box girder bridges, which I showed 5th order parabola, it shows 3-dimensional and 1-dimensional very similar. So why bother about 3-dimensional when you can do 1-dimensional in 2 hours? We are 3 minutes, probably 2 weeks if you're lucky. So in this equation, of course, Q naught is the rate of heat of hydration, which I mentioned earlier. If no heat of hydration, ambient conditions, only Q naught disappears. So that's very important. When you got a curve, you accurately differentiate it to get Q naught. That's in joules per meters, cubic meters per second. The joules per second is watts. So this is a couple heat generation when we deal with early age temperature modeling. Now on this equation, you can see if specific heat is C0, steady state is achieved instantaneously. So specific heat is heat needed to raise the temperature of 1 kilogram of material by 1 degree. For those in the audience, water is one of the unique materials on the planet. C for water is about, I think, 6,000. When it for concrete is about 1,000. So that's what, if you take a water tank in the heat, when solar radiation coming, water is a very big source of absorbing heat. Next one, please. Yeah, this is my personal prejudice. I am a finite difference man. I did a lot of work in the past till my consultancies. I do finite difference. Finite element would be good, but they are normally software packages. Now finite element, finite difference, I can do even on Excel spreadsheet. So thickness is divided into n layers, and so we get n+1 nodes. Next one, please. Next one. Yeah. So heat balance of interior, I just, most of you would know how to do what's a finite. It's very simple. Heat transfer coming from left and in, going to the coming from the right is in, going to the left is out. Difference is the plus the heat of hydration give the temperature rise. So it's very, very simple equation. And the finite difference, you can do it unconditionally stable. Any time state stays stable. We call it implicit, or somewhat conditionally stable, something called explicit. Those are in some publication I did 19, and there's a guy called Cook who did in 1982. Anyway, next one, please. So finite element realization for nodal temperature at interior nodes. So if you look at Ti-1 is I-1 node, temperature at time state J+1. And exterior nodes, it's interaction with the environment. That's how the equations come up. Next one, please. So then you can assemble overload temperature matrix. You write those equations, one external, one internal node, or two external and interior. You get n+1 equation. You solve it to get temperature at the end of each time step, and you march forward. So I do some on the Excel spreadsheet now, but it's unconditionally stable. Sorry, conditionally stable. So you had to select the right time step if you are using explicit method in the computer program or Excel. My implicit one in the MS-DOS program. Next one, please. Next one. Yeah, step 3. Assemble ambient data. I just give you this one because a lot of Bureau of Meteorologists in most of the countries are either disappeared or they don't do any work. They try to make money out of business, but they are not good business people either. So anyway, so you can develop ambient data based on some of the simple parameters they give. So next one, please. Relevant ambient data, the ambient data, we don't know ambient data in advance in motor care. Like in Sydney, I get weather 5 days in advance. Some countries you may not get, but still, if you got a computer or even a calculation pad, you can update your temperature generation in the pole as you measure the ambient data. Always there should be sensitivity analysis if you are in the design office. Your temperature won't be 30 degrees or 10 degrees. Now relevant data, mainly solar radiation, wind speed, ambient temperature, reflected. It's mainly on the walls because the brighter or clear surroundings will put some solar radiation back into the nearby walls. Next one, please. Ambient temperature. It determines the convective. Lower the ambient temperature, faster the heat loss from the hydrating mass. So mass concrete, that's QC. HC is the surface heat transfer. TS is the surface concrete temperature you get from your program, and TA is ambient temperature. That's TA is the TA and H are the ones we need to input. So yeah, more, as I said, most countries weather forecasters now only give very few data. They won't give hourly variation of the temperature or solar radiation at all. I don't know in Sri Lanka, but here now. Next one, please. So this is ambient the daily temperature prediction, how it varies with time for the hottest date in Sydney. I did this one 2000 based on T max, maximum temperature, and the T minimum given by the Bureau of Meteorology. So there are two models. That's how they look like. And I didn't put it because I didn't get client's permission. We put again measured. They are reasonably accurate. You don't have to be very accurate, but reasonably accurate. Next one, please. Then wind speed, as I said, it faster the wind going past your wall, it takes a lot of heat. So Billington 1965 produced this chart. So in this one, you can see even wind speed is 0, there is heat loss with Hc equal to 10. So when wind speed about 16, it's a lot of heat loss from the this in meters per from the hydrating surface. Next one, please. Solar radiation. You know, again, Bureau of Meteorology now they don't give hourly solar radiation, but some solar panel suppliers will give. But again, they use the same formula which I have given. I haven't given the formula. This algorithm I developed about 2 years ago. So they only give what is the total solar radiation for the whole day. They won't give hourly. So it's coming normally megajoules per meter square. Like Australia, we can get it free from the internet, from the Bureau of Meteorology. So when solar radiation incident on the surface, what is absorbed into the hydrating body is A is the surface absorption coefficient, and S is the solar radiation. Now, A is depending on the color. I'll give some typical numbers later. Next one, please. Again, this is the 3rd January 2002. Maximum Sydney total solar radiation. If you're running a solar panel, you make money that day. 34.4 megajoules per meter square. And that day, how the temperature, how the solar radiation incident on walls as well as the horizontal surface. So I developed a solar algorithm in 2021. You can see that two sort of knobs on the two sides are east and west facing walls, and the one on the middle is a horizontal surface. Horizontal bridge deck get more heat, volume as well as intensity compared east and west wall. North and south, not much. In here, Sydney, north side wall get more solar radiation in the winter. Next one, please. Again, thermal properties of concrete. Those who want to do modeling, I just give you some numbers. You know, so that's what I put this step as well. If you Google, probably you can get any number you want as well. Next one, yeah. Typical relevant thermal properties. As I said, water has a thermal conductivity. Normally saturated dry concrete is 1.4 joules per meters per second. To hardening concrete, like wet concrete, 2.2. So higher the thermal conductivity on early age concrete, it loses to the environment in a faster manner. The specific heat doesn't change much, 900 to 1100. Then surface absorptivity coefficient, this is how much solar radiation incidenting will be absorbed. If 0.35 white surface, 0.65 gray, and 0.9 black surfaces. So concrete is normally starting with 0.65 gray. After some time it's 0.9. So 0.8 is a good number. Next one, please. Step 5 is strength and stiffness in young concrete. This is very important when we do thermal stress calculation and compare potential for cracking rather than just temperature only. Okay, next. Yeah, next one, please. Tensile strength is developing with time as well in young concrete. so is the compressive strength and stiffness, E, Young's modulus. So if you got a temperature delta T, E is very important. That's what calculate the stress. E alpha delta T, I think high school or grade 5 lesson. So standard cylinder test in concrete want actual things happening in the hydration concrete because of that we are elevated temperatures. So this is called as maturity function. Small model we modified from CBF5P, the European thing. So this model will give with temperature, shear is tensile strength, dependency on the temperature as well as time. And similar relationship can be used for defining E as well. I didn't put the relationship because of the time limitation. Next one, please. Temperature, yeah, this one I put, yeah. So you can see the bottom two slides are standard temperature, compressive and tensile strength. Top two one are in the middle of hydrating body, strength as well as compressive strength as well as tensile strength gain is very faster. So it's very important when we do thermal stress calculation and compared with the strength. We look at the hydrating environment of the strength and the strength gain. Next one, please. Creep of early age concrete. As I said, creep early age can reduce the strength, is thermal stress by up to 50 to 60%. So what is creep in for a structural engineer doing with hard stuff? Creep is if you apply a load, there's elastic deformation, then in course of time, it deform as well. And one thing to note is creep is highly dependent on the time at which you load the member. Earlier loading, like 1 day, creep, they probably increase the deformation by a factor of 2. So that's very important to get a proper creep function when you do early thermal stress predictions. So the people have now, there are a lot of models early age creep, but we also did one 1995. It takes both the temperature and the time into account when at early age. Because early age you can see creep it should be high because it's still it is hardening. It's like a paste. Next one, please. Yeah, this example. The bottom one is standard creep test done under what you call 20 degrees and 80% humidity. Top one is same concrete mix at varying temperature up to 6 degrees. The creep factor is about 1.6. It's basically increased by about 160%. Next one, please. Step 6, thermal stress calculation. Yeah. Next one, please. Engineers, I think, avoid thermal stress calculations. As I see it, they leave the temperature part to a materials engineer. Materials engineer, again, not to discredit them. They have no idea what the stress is. So what you get is they develop the mix design, you pour it and it cracks. Then, it should be an engineer's job or both sit together and work it through. And it's difficult calculation. And modern engineers start Googling, but Googling won't take you anywhere. And even if you get the answer, it could be the worst answer in the world. It's like Googling symptoms for ailment on the web. Probably I should not be alive here. Anyway, most of us do if you belong in the Google. Engineers use guidelines as religious text. Syria C76, we use British Standard, we use that one. We know better than anybody else, but it's nothing. You have to use your own knowledge and training. And as I said, if people don't know how adiabatic hydration versus other hydration, what's the point using any of the models? Universities don't teach them at all because they know if you engineer go to a practice without knowing how to design a beam, they won't get a job. So they don't only teach you how to design a beam against applied load. Most universities I know of, but there may be few exceptions. And also somebody told 3 to 4 decades ago, control maximum average and differential temperature, you will be off the hook. But remember, not in today's DNC. You are not off the hook. You got the hook on the mouth, sir. Somebody need to tighten it. Next one, please. So thermal strain, incremental thermal strain. So just the simple calculation procedure. Thermal strain increment is alpha delta T. So in the bottom one, the equation alpha T time T at time T plus delta T minus T times T plus. We had to get the creep into account too. If you don't have the creep, you are overestimating everything. So that's what I put creep. Creep calculation is a little bit difficult, but on those the papers I cited, it gives some guidelines on how to do it. Next one, please. Yeah. So I think stress calculation. I just put this one. As I said, simple beam column example like Raft Foundation. You know, so you can say it's basically a wider beam. And so it's bending in the direction. So left is typical temperature gradient nonlinear. And then we have a uniform and the differential. And the last one is, I said, residual. That's what I think even ITC Tau in Colombo, they would try to minimize that differential a little bit, because that give residual stress. That's what a lot of surface cracking happens. So this is, we just need to understand the ambient temperature, hydration. This is basically what it is when it comes to beam column joint type member, raft or wall, you know, the beams, except, you know, the probably the complicated something like a generator housing, things like that. They are not beams, so they probably need a finite element stress modeling. Most of the things otherwise can be just this simple visualization. You can see the Priestley's papers I have written, tested, they all done not this simple model. Next one, please. So incremental thermal stress, again, it's a little bit of maths involved. As I said, for a given temperature gradient, including creep, you can calculate stresses from this formula. You can see the maths in that 1998. And RF is the external axial restraint. RM is the external flexural restraint. So if RM and RF are 1, it is fully restrained. You can see that equation delta sigma equal to E alpha delta T. And if RF and RM are 0, it becomes equal to the that residual stresses I talk about. Most software and engineers forget about. And then once we calculate the incremental temperature stress at a given time increment, then you do the cumulative bottom one to get the total stress generation at time, any given time. That's simply what thermal stress calculation is. Next one, please. Risk-based thermal crack control. Japanese, they spend money on research, and they like concrete too. So what they did, a very smart idea. Always uncertainty is involved. So they said, if you do a concrete work, come up with the risk-based thermal cracking potential. So we calculate thermal stresses, process I gave you, then tensile strength gain, maturity, calculate that ratio, and then say, depending on the imports of your structure, make sure that your cracking potential remain within those numbers. So TCI, thermal stresses with the tensile strength, should be less than 0.6 if when cracking is to be prevented. You know, I had to be very careful, concrete cracks, but it's a calculated, prevented. You know, this approach makes sense because we are dealing with uncertainties. And important projects, there is no answer, it doesn't crack, and it will crack. It's a potential only. So that's what I said, risk-based. Next one, please. Yeah, this is, I was partly involved with developing this. This is a curve we get. So what you do at that risk, potential thermal stress versus tensile strength or the x-axis, then you look at the probability of cracking. This has been developed on some actual measurements over 800 sites, so it's quite handy to do in risk-based. As I understand, even 3 decades ago in Japan, owners need this curve developed as part of their concreting QA and QC plan. Next one, please. Some practical applications, just to highlight, a few things. I think I got about 6 very quickly. First one, next one. Case 1, area with adiabatic. I just want to highlight, area with adiabatic. This sample we have measured isothermal as well as adiabatic. You can see the 2 different curves. Green one, it hydrates faster, and the red one is slow. Red one represents a concrete zone near the external, exposed to ambient. Green one is the inside. So using, Q for all hydration model, adiabatic is incorrect. It has a place, but then don't try to split hair with the fancy finite element modeling for sensitive structures. So as I said, not point using such crude models, whether it is Syria or whatever it is. Next one, please. On the same model, we applied for 2 volts, 600 and 200. You can see the difference in calculate thermal stresses. So the adiabatic give about 3.5 for 600 millimeter volt. Correct hydration model give about 2.7. So it's a big difference. So there's an error already there from using the wrong hydration model. Next one, please. Case 2, type and removal of formwork. So people think removal of formwork is only to get strength. No, you get some members thermal shock as well. So steel formwork allow heat to be lost because conductivity of steel is much higher. And when you remove the steel formwork, there's no thermal shock. But if you use wood formwork and suddenly remove it, you get a thermal shock. You can see the change in stresses on the one on the right, my right hand side. So formwork removal and type of formwork need a little bit thinking rather than just say formwork removal is to do with the concrete getting the strength. Next one, please. Case 3, creep helps relaxing stresses. As I said, anybody not using the benefit of creep relaxation can come up with crazy designs when it comes to Rio. So in this case, 600 millimeter volt stress distribution, the tensile, you can see the same temperature, the development of calculated strength, stresses are much higher than the bold line compared with dotted lines. So that's one reason. Probably when you get some of the structural programs and then put these temperature gradients and calculate stresses, you get very crazy numbers, and then you start putting Rio as well. Some Rio is so heavy, wondering why it is when we have uncracked concrete 30, 40 years ago without any reinforcement sometimes. Okay, next one, please. Thermal stresses versus tensile strength. As I said, this is done for Canning Dam in Western Australia. It's a gravity dam. It had alkali aggregate reaction, and we put, I think I did a presentation about 6 months ago. We put 91 strand cables drilled through the dam and 130 meters into the foundation. Each cable had 91 strands, and each cable carried 2,250 tons. I think that's the weight of a US largest aircraft carrier. And there we couldn't take any chances on the anchor block, because if it cracks, there's no guarantee that the anchorage would be okay. So we did a very, very comprehensive model. In the top graph shows, the top one shows, the darker one is the tensile strength, and the bottom sort of wavy one are the thermal stresses near the surface. And in this case, I think daytime temperature hit 35, at night 15 degrees. So what we did is at night, in the evening, we put plywood um, to keep the differential temperature down. In this case, all the thermal stresses are below the tensile strength. So it never cracked. And we were very happy. Otherwise, a lot of Rios, we can't put that many Rios, already got Rios, as well as the chances of cracking should be limited even if we had Rios, because of the nature of the beast. You know, if one of our anchors give away, that will break the dam in half. Next one, please. Buttressing of concrete dams. For example, those in Sri Lanka, probably they buttress the Nalanda Dam, like 2012. Yeah, in that dam is unstable according to modern factor of safety. So they went and put concrete behind. And why I put that is you had to be very careful when you buttress a dam. I wrote a couple of papers, and currently involved with the largest probably buttressing dam in Australia with 8,000 cubic meter of structural grade 40 concrete, making a buttress on the dam supplying water to Sydney. So it's a big job, and you can't take charge. The thing is, you put the buttress to strengthen, but then you can't crack the existing dam. Said, oh, sorry, I cracked your dam. So why it happens is when the buttress cools down, it put tensile stresses into the existing dam. So we need to make sure the existing dam risk is not compromised due to any construction. That's the law in most of the states in Australia when it comes to dam engineering. You can never compromise the existing risk profile. So basically, you can't crack the dam when you come to fix it. Next one, please. On that one, we had to make sure that thermal stresses are well below the tensile strength. So this is a typical graph showing dotted line the thermal stress, and the bold line is the tensile strength. So I think in this case, we had to further cool down the concrete and alter the mix because we thought it's going too close based on this. If you look at the Japanese risk base. Next one, please. Yeah, multi-layer concreting is a myth. I think ITC Tower too, they said they were pouring concrete in multi-layer. I think probably that's the wrong thing to do. That's okay. As I said, there's a belief that layering is a good idea to keep the temperature low in thick rafts. You know, that's what people have told them or parroting. So as I said, same has been done in ITC Foundation in Colombo too. So they, I think, poured concrete in 1 meter thick layers between gap between each layer because they want to keep the temperature rise down. What engineers forget is that it's still going back. The thermal stress is created by internal and external restraints. In multi-layer concrete placement, the hardened bottom layers restrain the new layer. So that's what we don't want it, but we created it by unknowingly because we want to keep the temperature low. So next 3 slides, I will show you some calculation I did as part of anchorage block of a cable stayed bridge up to 5 meter thick. Just to show that this is the last slide. Don't go in the tangent of temperature control when you come to serious projects. It worked in the past because same mix. Now things are different, and you can put any amount of Rios, but Rios is okay. Whatever the things, you know, is small. But theory, if temperature exceeds stress, thermal stress exceeds the tensile strength, thick members crack will go through. I have seen those things. You can put a pen on this one. So in 40 or in 50, it just you sleep well at home until next following day morning probably. Next one, please. So this one, layers of 1 meter thick. This is a simulation I did with 1-dimensional heat transfer and the thermal stress calculations. So we compare layering versus, you know, continuous pour. Of course, continuous pour has a time, you know, you can't put it, wish it in place at once, but we don't leave it a gap between each layer. Okay, next one, please. Yeah, so the bold lines are the ones done with single layer, and the dotted line is 1 meter layer with 3-day gap in between. Of course, temperature dropped by about up to 40%. That's a good news. So let's go to the next one. So when we look at it, it's the other way around. The tensile strength, yeah, tensile single stage and multi-stage. You can see the 5 meter multi-stage temperature is somewhere around, you know, 2.5 MPa compared with single stage all in compression. So as I said earlier, temperature is low, but you know, your stresses are, tensile stresses are much higher with multi-stage. This has been tested, I saw recently in a German journal as well. Not to, probably they copied my stuff, but they never acknowledge it. But you just need, doesn't need my stuff, just need to look at when it's a restraint. So multi-layering, you create the worst scenario for the thermal stresses, which is ultimately responsible for cracking. Yeah, next one, please. Thermal crack control measures. Yeah, look at it. Just a couple of them. Yeah, next one, please. So typical, the most obvious one is placing temp. Of course, you need to, when you order cement, don't say I need minimum 300 kilogram cubic meter per concrete. Contractors are smart. They say minimum, they give you extra 2 bags of cement. They don't want to take a chance. It cracks. They say, engineer, you said minimum. You didn't say maximum. So I gave you two bags. Bad luck, it cracked. That's your fault. So keep the minimum cement content minimum you need. And also, I didn't put it, don't trust your fly ash or silica foam. As I said, they sometimes produce more heat than ordinary Portland cement. Western Australia, about 20 years ago, the guy said marine cement, 80% slag. Some clients pour them concrete crack next day, where they didn't have a single problem with ordinary Portland cement. You know, I am still working or work for the Western Australia Water Corporation for 20, 30 years. Sometimes they crack because they send it to the mill to grind it very fine. So fly ash slag produce more heat than the ordinary Portland cement. I'm pretty sure in Sri Lanka too, they have fly ash. And again, in this one, that ITC tower, I don't think fly ash work. As I said, if I were you, I would buy beer and drink it. You get 5 cents back from the can. So don't trust the cement, what is said in the cement bag, or the rep coming with a nice suit and a tie and say, I got, you know, sustainable and all that, buzzwords these days. So place in temperature should keep as low as possible, and should always, of course, minimum cement. And these are the typical costs in Australia, 2014. Nice. You can keep the aggregate shade, it's cheap, can reduce the temperature by 40 to 5 degrees centigrade, doesn't cost you anything. Then acid chilled water for $0 per centigrade, so about 6 to 7. Then add crushed ice. Most dam projects use crushed ice. And if worst case, you can use liquid nitrogen. Liquid nitrogen is the one doctors use for burning things on the skin. And it about 3.5 Australian dollars per centigrade drop. So if you get 30 aggregates everything at 30 degrees, you can drop it to 20, but liquid nitrogen. So 10 will cost about $35 per cubic meter. So mass concrete is about 150. So 35 divided 150 is about, I think about I don't know, 3 by whatever, 30% more costlier than just cement only. And it's nowadays very difficult to find a large liquid nitrogen plant as well. So probably they need to be bought from overseas. Next one, please. Summary of my presentation. Time to look beyond merely determine the temperatures and maintaining below maximum and differential values. Because somebody said, 45, 4 to 5 decades ago, things have changed, faster construction, different litigation, and also different cement types. And we are asking for 120-year design life, so probably more cement to get the permeability and the diffusion coefficient low. So they all in one game plan. And always, where possible, please do hydration modeling and real modeling has no place for adiabatic models anymore. They work, probably will work, but you have no way to explain when things go wrong. One getting popular is hotbox. As I said, there's a French standard for that. I mean, only in the project in Philippines that they use French, a hotbox, and also there are some correction factors. I think the chap in Hong Kong, what's the Public Works Department, has developed quite handy. We are using for some dam projects here. So hotbox, you can determine adiabatic and non-adiabatic isothermal with those correction factors. Otherwise, you can use a finite element model to calibrate it. Don't be a slave to guidelines. So standards, whatever the CEO, BS, EN, or whatever, client engages you, not the guideline. And guideline developed somewhere probably 1,000 kilometers away. They engage engineers, not a guideline. If they are guideline, they can use a fifth grade student to repeat the guideline. It's easy. Thermal cracking is very litigious. They sue you. So because the contractors need to give a clean concrete product to the client, and guideline or divine power won't help. So you had to know what you are doing. Irrational approaches can be result in expensive design in vain. As I said, always buy beer and drink it, you'll get 5 cents back. That's what I would do probably after this presentation. Anyway, thanks for listening to my presentation. I don't know what's the time now. But when we finish.
Yes. Yes, sir. I have one question. There's one question in the chat box. I said, for multi-layer concrete, what about each layer place crack control bottom reinforcement?
Crack control?
It's not clear that much.
No, you need to look at both surfaces. As I said earlier, bottom surface will get tensile stresses. So you are trying to reinforcement in thick concrete, as I say, is feeling good only. I have seen a lot of rears till they crack. So please follow that Japanese guideline, which is what we have been doing for years now, since this modern guidelines. Any temperature gradient you put, still you will be well off the hook. It's still how rear work in young concrete is. BP Hughes and few others in UK have done some work, but how it really behaves is not well known when it comes to mass concrete. So if you got concrete, rather than, of course, if it is on a rock foundation, it's different. If it is in soil, because they axially unrestrained, you should do the both things, and most likely, unless DEF is an issue, in your case 85 is still you're on the red zone for DEF, so probably you didn't achieve both. Temperature you didn't achieve, and if you calculate thermal stresses, probably you are worse than single monolithic pouring.
Another question is now for usual concrete elements which has lesser thickness, we are doing water curing likewise. So when it comes to concrete elements which has a larger thickness, how you should treat the surface? What steps?
Surface cooling, you have to be very careful, as I say, thermal shock. And if you look at durability perspective, I think if humidity drops below 80%, hydration stops. So it should be cured. So what happened? Durability is governed by the strength and the hydration, proper hydration of the surface layer. So if no water in a dry weather, irrespective of temperature, you had to cure them. Did I answer? Otherwise, in some walls, try to keep the cooling down liquid, not don't get liquid nitrogen, chill water, aggregate, pouring sequence. Hot days avoid pour concrete in the evening. That's the cheapest option. And worse come to worse, there are projects where you put cooling ducts. Let's say recycled water. I have seen that in sewerage plants. Very high cement kind of 550 for durability issues. So they have putting steel pipes and send the cool in the water at the middle and recycle water.
Yes, question related to the same thing. When the thickness of the concrete element is very high, we have a huge temperature increase in the core, but we have some practices are there. The surface it is not cooling. It is the heat is keeping to keep the difference in the temperature reduced in the core and the surface.
Yeah.
So in that case, what standards or what approaches?
And as I said, if you look, you need to look at the sensitivity. As I put that wood formwork and steel formwork. So sometime basing is the no polystyrene during daytime. So the heat is lost progressively. At night, if you're getting too cold, you put the polystyrene back. So you need to manage both. Differential is one thing. If you got what you do, if you try to reduce the differential, you reduce the heat loss. You can see when it cools down uniformly, elevated, you will get true depth cracks. So what do you like to have? True depth cracks or surface cracking? In a water retaining structure, true depth cracking is the end of the structure. As I said in the desal, cracks with true depth, because they left it to the contractor to do the design.
Okay. And there was another question in the chat box. He has asked any sustainability high concrete. That's what he has put in the chat box.
Sustainability?
High concrete. He might be asking about any suggestions or modern approaches.
Yeah, but sustainability is okay. That's a very sellable word, but you just need to get first thing. We are here to make a durable structure. So as I said, some people send slag or fly ash. They produce more heat than anything else. So sustainability should be there. But the first one is to get a structure which is going to be durable for 120 years. So as I said, the one sustainability good cheaper one is not right minimum cement. Minimum cement is 1,000 bags of cement. So you have to give minimum and maximum requirement, not to overkill on the minimum, because some engineers think putting a minimum, they are going to put screws on the contractor. No, he will give you extra cement, it's cheaper. And it will crack. Then if crack, he said, you ask for minimum, I give you extra cement, why you are complaining?
I think that's all in the chat box questions. If you have any other questions, you can put into the chat box right now. There's one. How is thermal stress strain works in situ board piles in relatively large diameter?
In situ?
Board piles.
Yeah, okay, in situ board piles. I was involved in I didn't put that in the project here. Some of the guys, Sydney would be 2.5 meter pile, socketed in rock in the Sydney CBD. I think I put that slide in the last talk. Temperature, because it's a high load transfer, axial loads from a very tall building going through existing tunnels, and we rely on the shaft skin friction. And we put real restrictions on the how to calculate. Because what happens if temperature is high, when it cools down, it will separate from this shaft friction, the interface. So there is no shaft friction. So we make sure that I think they run cooling pipes through the pile at the middle. And allowing for that, not to allow for that delamination. I think that end bearing is not affected, but it will affect if you are relying on piles on socketed in rock. Soil probably not, because soil change in water table will still bring the whatever the design has assumed for skin friction, but not in rock socketed piles now. I think that's the question. I think answer.
In the chat box, that's all questions.
Okay then.
It seems and so have put big effort in creating these slides. Actually, it was very informative, and there are a lot of things to get from the slides itself. Luckily, we are having recorded this lecture, and we will upload into a YouTube channel, and this will be very useful for all the practicing engineers in here as well. Thank you very much for that, sir.
Okay. Thanks a lot, guys. See ya.
And I would like to invite Engineer Nalaka to do the vote of thanks.
Good evening, everyone. Can you hear me?
We can hear.
Good evening, everyone. I stand before you today with gratitude and appreciation for the incredible opportunity to attend the webinar on heat of hydration effects in concrete placement, theory and application, presented by the esteemed engineer Dr. Nihal Uttarana. This event, thoughtfully organized by the Civil Engineering Sectional Committee of ISL, has proven to be both timely and enlightening, shedding light on the modern practice in our field. First and foremost, I extend my heartfelt thanks to the chairman, Civil Engineering Sectional Committee, Engineer Mrs. Kamala Gunawardana, for her unwavering commitment to promoting knowledge sharing and professional development within the civil engineering community. Her dedication to fostering the platform for such informative webinars is truly commendable and inspires us all to continually seek growth and excellence in our respective fields. Dr. Nihal Uttarana's expertise and passion for the subject matter were evident throughout the presentation. His in-depth exploration of the heat of hydration effect in concrete placements opened our eyes to the crucial roles this phenomena plays in ensuring the durability and structural integrity of our construction. The theoretical insights and practical application shared during the webinar will undoubtedly have a positive impact on our future projects, enabling us to make more informed decisions and adopt the best practices in our work. Furthermore, I wish to express my gratitude to the entire organizing team and the coordinate, Engineer Banduka, for their commitment and putting together this enlightening event. The seamless execution and the attention to the detail have contributed to making this webinar is resounding a success. I would also like to thank the ISL Secretariat, Publicity Department, and IT team for the hosting the arrangement. I must also acknowledge all the participants who joined this from various corners of the civil engineering community. Your active engagement and insightful questions enrich the learning experience for all of us. In conclusion, I am grateful for the opportunity to have been a part of this webinar. The knowledge gained here will undoubtedly elevate our professional endeavor, and I am excited to implement this learning in my future projects. Thank you once again, Engineer Dr. Nihal Uttarana, and Chairman Engineer Mrs. Kamala Gunawardana, the Civil Engineering Sectional Committee, and all involved parties for the making this event possible. Let us continue this strive for excellence and work together to shape brighter and more sustainable future for the civil engineering. Thank you all.
Thank you, Engineer.
Thank you, Nihal.
Okay, thanks. Come up.
Okay, thanks.
Thanks,
Okay,
Bhanuka. Okay,
thanks.
yeah.
Yeah,
Okay,
it will-
take care. Bye.
Thank you, Dr. Kamalachiri, for your presence. Thank you.
See you later. Thanks.
Thanks. Okay, bye. Good night.
Bye.